So let's start off with the absolute most basic thing you can do in LTSpice. We're going to make a single voltage source and a single load and measure the values from that. For something simple like that, that doesn't have capacitors, doesn't have inductors, doesn't have other active components, the easiest method is to do a DC operating point analysis, which more or less just spits out the instantaneous calculations of what's happening right now. It has nothing to do with time. Let's create a new schematic. File, save as, give it a name right off the bat. Now in LTSpice, the main bar that you're going to be using most is going to be everything from this pencil, which draws a wire connecting components to each other, the ground, a handful of common components, all the other components that you can possibly add to it, rotating things, undoing, redoing, and running your actual simulation. I'm going to grab a power supply, a voltage source. So you first go to the component, and you can do a quick search, text search, for approximately what you're looking for. We're looking for a voltage source. Press enter, and place it on your schematic, wherever you want. Once you've placed one, it automatically allows you to place many. If you are done placing voltage sources, you can press escape and do other things. If you've added components that you don't want, you can press delete, which turns into scissors, and then click on what you want to get rid of. Press escape to get out of the delete. Now that we have a voltage source, we can grab a load resistor and place it on the board. Right now we don't need more, so press escape. Right click on the voltage source, and you can tell it what the voltage is. For now we're just doing a static analysis of constant values. So this value is going to be, for us, 5 volts. The resistor, let's make it easy, and we'll right click on the resistor and make it 1000 ohms, or you can just simply type 1K. LTSpice understands that K means 1000. Connect the components with the wires. And although this looks complete, one requirement for LTSpice to do anything is for us to identify what's known as node 0. It's the 0 volt reference, or the common, or basically the starting point for all the calculations. And it's also going to be the point of reference for all voltages that you place on your trends. That is this, the ground symbol. You can zoom in and out with the mouse scroll wheel. And it doesn't matter too much where you put this, but I like to put it near the power supply if I can. Escape, draw a line, connecting that to our 0. Since we're just looking at the DC operating point and we're not trying to measure values over time, we go to Simulate, edit the simulation command, and choose DC operating point. This is also going to make us put this little symbol here on our schematic. It doesn't matter where we drop it, it just needs to be on it. Finally, simulate. So we can click the little running guy here, or we can go to simulate and click the little running guy there. The calculations are run in the background, and it shows us what all of the voltages and currents are. So voltage at node 1. Node 1 is this top line right here. I know that it's the top line right here because we've identified node 0 as this, the ground symbol. So the voltage at node 1 here, this line, is 5 volts. The current through R1 is 5 milliamps. And the current through the voltage source is minus 5 milliamps. Now the minus 5 is a little confusing. The reason it's negative is because LTSpice is calculating the current top to bottom through the components that are on the screen by default. We can change that, but it's not really necessary. It's just something that you need to bear in mind. So the voltage source, even though we know that the current is coming out the top, so it's flowing up, it's being calculated from top to bottom. So top to bottom, the current is negative in the opposite direction. The load current, the load resistor current, on the other hand, makes sense because top to bottom, from 5 volts to 0 volts, the load resistor has a current of 5 milliamps through it. And together this makes sense because the voltage supply is 5 volts and it's a completely series circuit, so all current from the voltage source is passing through the resistor. Now we can make this a little bit more descriptive. We can right-click on the label of anything that we want to change. Instead of V1, we can rename it vSource. Instead of R1, we can rename it RLoad. We can rename it anything we want as long as the resistor starts with an R. So now, when we run the simulation, rather than V1 and R1, it's going to come up as RLoad and vSource, and the currents through them. This voltage on this line can also be renamed. So if we right-click on the line, we can label this net, and we can call it anything we want, but in my case I'm going to call it V+. And just place it in contact with that line. If we simulate it now, the voltage of V+, instead of node 1, which is difficult to suss out sometimes, is 5 volts. The current through the source, looking top to bottom, is minus 5 milliamps, and the current through the load resistor, looking top to bottom, is plus 5 milliamps. So far, so good. So now, let's make this a little more complicated. Let's add another resistor and turn this into a voltage divider. So press delete and delete this wire. Grab a resistor and add it to your schematic. Right-click on the resistor and give it a value. Let's say 3,000 ohms. F7, remove this label temporarily. Finish the circuit. F7, move the label onto the net. And I'm going to rename our load to be R2. I'm also going to bring out a line which will represent our output voltage across R2. I don't have to do this. I'm just choosing to. So if we now simulate this, we see the voltage from the supply is 5 volts. We see the voltage from net 1 is now 1.25 volts. I don't like the net 1. It's just, as soon as you get a more complicated circuit, you'll understand how confusing this can be. So let's give this a descriptive name. Instead of an arbitrary name that's just the order that the line was put, let's call this, right-click on the line, label the net. We're going to label it Vout, and then place it on the line. Now when we simulate it, our supply voltage is 5 volts. Our output voltage across R2 is 1.25 volts. The current through R1 and the current through R2 are of course identical because they're in series, and they are 1.25 milliamps. And the total current from the source, because it's also in series with the two resistors, is identical, just in the opposite polarity. And we understand why, so we're not bothered by it. Now, if we wanted to make the schematic a little bit more user-friendly, especially for report generation, and not constantly be cross-referencing these net calculations, this net report, to the components, we can actually get rid of this. Press Escape. And just like with adding the labels V plus and V out, we can also add data. Right-click on the line and place Op Data Label. Right-click on the line and place Op Data Label. So now we don't even need that text report to tell us what's going on in our circuit. And of course, everything here is easily changeable. So if you wanted to change the 3K resistor to a 10K resistor and see what happens to the output voltage, you just change the value, rerun it. It does the calculation. Vout is now 0.454 volts, and the labels are updated. After running the simulation, you can just cut and paste this into a document. It's plain text. So I'm going to save this, and then I'm going to save a copy. And we're going to call this Prelab 1B. So let's go one step more interesting and create a circuit with something more than just a few resistors. I'm going to delete pretty much everything. I want to add a transistor. So we go to the component library. And in the component library, you have many standard components. You have LEDs, you have chips, you have power supplies, and of course you have NPN transistors. So let's bring a transistor, a generic transistor, into the circuit. We'll add a resistor to the collector. And we'll add a second resistor that's going to be the base. And make a few connections. So we'll bring that to the resistor connected to the collector, and the resistor connected to the collector, the emitter connected to the negative of the power supply, the base to a base resistor And for now, we're just going to connect the base resistor straight to the 5 volts. We're going to call R1 our load resistor. We're going to call R2 our base. Our load resistor is going to be 330 ohms. And our base resistor for now is going to be an arbitrary 100,000 ohms, 100K. What happens if we simulate this? Our supply voltage is 5 volts, and we have a couple of arbitrarily named net voltages with a collector current on transistor Q1 of 4 milliamps, a base current of 42 microamps, and an emitter current, which of course is the total of the collector current and the base emitter current together. So IC plus IB equals IE. Once again, these N1 and N2s are a little bit confusing, so let's change those labels. I'm going to bring a line out, and I'm going to call this V out. Right click, label net, V out, and attach it to the line. I also want to see what the real-time value is, so we can immediately right click, place a data label, which hasn't been calculated yet, at least not as V out. It was calculated as one of the N1 or N2, but we don't know which for sure. And just for the fun of it, we can put a data label on the base, which we already know is going to be somewhere on the order of 0.7 volts due to the base emitter PN junction needing 0.7 volts to even turn on. But let's find out what this arbitrary generic NPN transistor is actually doing. So now if we simulate this, V out is 3.6 volts, which tells us that there's 3.6 volts across the transistor, which is not 5 volts, so it's not off, and it's not 0 volts, so it's not being saturated. Press escape, and you can see that the voltage with respect to this ground symbol at the base of our transistor, in this case, is 0.8 volts. Our load current is 4.2 milliamps, and our base current is 100 times less that. So the beta of this transistor is apparently 100 in the model that LTSpice is using for a generic transistor. Now certainly if we want to, we can simply play with the values of the resistors and get different numbers. But let's go again one step more interesting and simulate something that changes over time. So rather than having the base of the transistor be fed by a 100K resistor connected straight to a solid 5 volts, and of course the load resistor is a solid 5 volts, so as soon as power is applied, it turns on, it stabilizes at some operating point, which we've just calculated, and then stays there forever and ever and ever. But let's say we want to feed the transistor different values and see how it reacts over time. There's nothing stopping us from changing this source to be an AC source, but then that would also affect the voltage that's being applied to the load. I don't want to do that right now. I'm just going to add a second source so that an AC waveform is applied to the base of the transistor. So press delete and get rid of that. And I didn't leave myself very much space, so let's move a few things. F7. I'm just going to move the voltage source over, and the ground, and reconnect things. Delete, 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 delete. I'm going to bring in a second source, a second voltage source. Set it here. I'm going to rename this VIN. I'm going to make it an AC waveform. Now if I wanted a DC value that I could change, I could simply put in a number here and it would act like a static voltage source powering the whole circuit. We want to make something more fun. So go to Advanced, go to Sine Wave, and we're going to create a sine wave that has a peak-to-peak voltage of 5 volts. I want it to swing from 0 to 5 volts. So we want an offset that's half that, 2.5 volts, and we want an amplitude of 2.5 volts so that it swings from 2.5 plus 2.5 to 2.5 minus 2.5. And we're going to give it a frequency of 1 hertz. So 1 cycle per second. I'm going to move this little label here off the circuit and move the power supply just down so it's easier. Connect it to the rest of the circuit. The commons are shared, but the output of this voltage is going to go to the base resistor. Now, because we're going to be making observations of a changing circuit, we're no longer working off of the DC operating point. So we can delete this. And instead, we're going to replace it with a transient analysis. So edit the simulation command. And instead of the DC operating point, we're going to create a transient that goes from 0 seconds to 1 second. 1 full cycle. Now, for transient analysis, some of this is not useful. The output voltage readout, for example, if I can just delete that. And this voltage, although it should basically be 0.8 volts at all times, I'm also going to delete that. When LTSpice does the transient analysis, what it is doing is it starts off at time 0, calculates all the values, increments a small fraction of the time that you've set for the simulation time to end, recalculates, moves forward in time, recalculates, moves forward in time, until it has calculated everything that happens in our case, 1 second, but the time is entirely up to you. After those have been calculated and stored, you can review it, similar to reviewing a data log. So when you first do the transient analysis, when you press run, you're going to get an empty chart until you click something that is interesting, like the voltage. Now, when you see this red probe, it's a voltage. When you see this, it's measuring current. You can read the current on any component, and you can read the voltage at any point. So if we read the voltage by clicking anywhere on this line, it's just going to give us a straight trace from 0 volts, from 0 seconds to the 1 second simulation time that we determined. And it's going to be a static 5 volts all the way along, because this source is a DC source. We can add more traces to this chart by clicking other points. The output of this is going to be a sine wave with an amplitude of 2.5 volts and an offset of 2.5 volts. So the AC waveform is going to go from 2.5 to 5 to 2.5 to 0 and back up to 2.5, keeping it positive at all times, and repeating after 1 second. We can continue adding traces to this chart by clicking other things that are interesting to us. But it does make it a very, very busy chart. Voltages are on one side, and the current scale is on the other side. If you want to simplify this chart, you can simplify it by clicking one point twice. Not a double click, a slow 2 clicks. So the first click sets that point, and then the second click removes everything else. So we're back at 5 volts. So if we only wanted to see what Vin was, we could click once, click twice. If we wanted to see the base current, we could click once, click twice. If we want to see the base current from the voltage applied to the base, we can click and click and click. Now when we look at this trace, the first obvious thing that stands out is that where the blue trace is a complete sine wave, the green trace is not. It reaches a low point and stays relatively flat before taking off again. This is because in order to even conduct from the base to the emitter through an NPN transistor, you need that 0.8 volts. Below 0.8 volts, no current flows. So the voltage rises from 2.5 volts to 5 volts, back to 2.5 volts, and as it approaches 0.8 volts, the transistor turns off and stops conducting, and the current falls to 0. And then the current begins to conduct again as the voltage rises above 0.8 volts. If we look at the input voltage and compare it to the output voltage, a similar thing is seen, but inverted. Because with the transistor, when the transistor is off, no current flows. The load resistor has no current flowing through it, so the voltage drop across the load resistor is 0, and the voltage drop across the transistor is at its maximum point. As the voltage at the base increases, the current through the base emitter junction increases, allowing 100 times more current to flow from collector to emitter. The increase in current causes the load resistor to have a larger and larger voltage drop, resulting in less voltage seen across the transistor, resulting in V out going down as V in goes up. You'll see this effect again when you do Lab 3 and you get to the NOT gate. But in this case, we're actually seeing an analog value that continuously changes, as opposed to the digital logic circuit, where we are either connected to 5 volts or 0 volts, and nothing in between. So let's compare the base current to the load current. 1 click, 2 clicks, and 1 click to add both. And you can see that the base current is significantly smaller than the load current. Unfortunately, they're both on the same scale right now, so you can't see the specific voltages. You can always zoom in to see that the load current peaks at about 4.16 milliamps, and the base current should be 100 times less than that. Right click, zoom to fit, zoom in, and 42 microamps, as expected. Now, although this particular circuit is pretty useless, in all honesty, if you did want to output the values and analyze it offline, what you can do is you can either click what you're interested in. Let's say 1 click, 2 clicks. So we have the source voltage, we have the input voltage, we have the base current, we have the load current, and we have V out, all on the same chart. Right click on the chart, go to File, and export data as text. The points that you've clicked on the schematic are already highlighted, and what's highlighted is what's going to be out into a CSV file that you can bring into Excel. But if you did want to add a few more things, like for example the current being supplied from VN, although that's redundant because we do have our base, let's just say we wanted it. You could hold Control and click. If you didn't want it, you could hold Control and deselect it. Once you have what values you want spit out to the file, you save it wherever you want it. You can rename it to something else, like CSV, and save. So now if you go to the subdirectory and you open it as a text file, you'll see the time and the voltages at the points that you specified. If you rename the file to CSV or just simply open it up in Excel, you can create a chart of the values. And perform whatever post-simulation analysis is required. Now, as a final note, in the lab, the professor is requesting a 1N4001 diode or equivalent be used in your rectifier circuits. So when you're creating the circuit, let's just modify this useless circuit with some more useless parts. Let's say we wanted a rectifier diode to be placed at the base of the transistor so that it never gets a reverse voltage. You can start off by grabbing the standard diode, rotating it to point in the direction that it needs to point, and dropping it in place. Then right click and pick new diode. And we need at least a minimum current, so let's start by sorting by current. If we sort by current and go to 1 amp, the first one that can handle 1 amp can only handle 20 volts reverse voltage. The 1N4001 can handle 50. So let's find the first one that's 1 amp and at least 50 volts. So there's one that has a 50 volt rating, the RB160MM50. And if we take a look at that diode's datasheet, although this wouldn't be appropriate for a breadboard because it's an SMD component, the details are a reverse voltage of 60 volts and an average rectified forward current of 1 amp, which does fit with our 1N4001 spec. So we could use this in the schematic, but if we were to put this out into a physical product, we would either have to design around the fact that it's an SMD component, or we would have to find a through-hole equivalent, the kind of component that has legs that can stick into a breadboard. Either way, let's just accept this and use it for now. The same pretty much goes for any other component. Let's say you wanted a Zener diode at the output to clamp the maximum voltage. Rotate, pop it down, right click, pick a new diode. The type is a Zener. We want the Zener voltage to be, let's say 8.2 volts. We can look up the data sheet to find all of the details about this part we want, but I'm just going to grab this particular part for now. And I'm going to move it. And connect it. And the part you choose will have different characteristics, which will change the output. Being that this is an 8.2 volt Zener voltage, we need at least 8.2 volts at the output to show any effect. So I'm going to bump up the source to 12 volts. Run a simulation. And we can see what happens. Likewise, we can choose a specific transistor. 2N2222, 2N3904, very, very common in the lab. The 2222 can handle 0.8 amps. The 3904 can only handle 0.2 amps. The FT849 can handle 7 amps. And a quick datasheet lookup will tell us everything else we need to know. FZT849. FZT849. 30 volt NPN, medium power, high current transistor. SMD. You can put 3 watts through it, 7 amps. And the typical DC current gain is between 65 and 200, depending on how much current is being passed.